Hello and welcome to my science tutorials. In today's video, we want to look at pressure. Now before we begin, if you're new to the channel, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials. Alright, so let's begin by looking at what pressure is. So pressure can be defined as the force per unit area. So we define pressure as the force per unit area. So if you want to represent this mathematically, it means that mathematically we are saying that pressure is equal to force over area, where our force here, let me rewrite that, where our force is measured in newtons. So our force is measured in newtons, capital N, and our area is measured in meters squared. So what this means is that when we are given a question and we have to calculate the pressure, we need to make sure that the force is in newtons, okay, and then the area is in meters squared. It is very, very important. Now from this expression we can see that pressure, or we can make some deductions. We can say pressure is directly proportional to force. That is, pressure is directly linked to the force. So the higher the force, the higher the pressure. And then we can also say that pressure is inversely proportional to area, which means that if we have let's say a material or an object that has a very small area, because of this relationship, pressure and area being inversely proportional, small area means there will be a high pressure at that particular area. This is very true, as we can see some examples in real life. For instance, you can see that a pin, because it has a very small surface area with a minimum amount of force, is able to produce a very high pressure. Okay, so you can see that because the surface area of pin is very small, you always, mostly with a small force applied, you realize that the pressure exerted onto that particular surface area is very high, or it can be able to penetrate you. While if you take a pen, let's say a pen, the tip of a pen, because the surface area of the pen is the tip of the pen is a little bit bigger, the pressure over there, or the pressure applied, is very small. Okay, that is unless you increase the force very largely before the pressure will also increase. So what it means is that if we have a very large area, that area will exert a very small pressure onto a particular surface. And if you have an object with a very small area, that small area will exert a very high pressure onto a particular platform. Now before we continue, we know that area, let's just do some quick recap. Area is length times breadth. Okay, so let's keep that in mind. All right, so let's have a look at some examples to see how we can apply this formula that we are saying pressure is equal to force over area. Let's see how we can apply some of this formula to solve some questions. So let's have a look at the first example we have for this tutorial. So we have a plastic block weighing 25 Newton, has dimensions 34 centimeters by 25 centimeters by 10 centimeters. What is the greatest pressure and the least pressure it can exert on the ground. So let's have a look at the solution to this problem. So write down our solution. Now the first thing we have to do is to write down all the parameters that we have. Then from there we can go on and see if we can solve the problem. Now we were told that a plastic block of weight 25 newtons. So our weight, okay, which is equivalent to our force, is given to us as 25 newtons. So we have 25 newtons, and then we've been given a dimension of the plastic block. So the dimension is 34 centimeters by 25 centimeters by 10 centimeters. Okay, so let's try and draw the box. So let's say this is our box. Let me draw something over here very quickly. Okay, so let's assume this is our box. Okay, so I'm going to use this side over here since it's the longer side. I'm going to give that the 34 centimeters. Okay, so I'm going to give the height over here the 25 centimeters, and then I'm going to give the width over here. I'm going to give that the 10 centimeters. Okay, now if we look at this particular block, we realize that we can have quite a couple of areas for this particular block. So let me denote that with a different color. So we can have area 1. So this surface we can have here, the surface over here as area 1. We can have the surface over here as area 2. Then we can have the surface at the top over here as area 3. So it means we have 3 different areas for this particular surface. Now, in order for us to calculate the pressure that each of these surfaces can exert on the ground, we first of all need to calculate the area of these surfaces. So let's go ahead and look at area 1, area 2, and area 3. So calculating area 1. So area 1 is equal to length times breadth. And if we look at it, for area 1, we are dealing with the length, which is 34 centimeters, multiplied by the breadth or the height, which is 25 centimeters. So we have 34 multiplied by 25 centimeters. That will give us 850 centimeters squared. Now remember, we said that the area is supposed to be in meters. So if you like, you can convert the 34 centimeters to meters first, then the 25 centimeters to meters first before you do the multiplication, and then you get your answer. Else, you would have to convert 815 centimeters squared here to 2 meters. So let's look at that. We know that 100 centimeters is equal to 1 meter. So if we want to have meters square as our answer, we will have to square 100 centimeters. We square this side, then we square 1 meter as well. Okay, so sorry, the square is supposed to be outside. We square that as well. So this will give us 100 times 100, which is equal to 10,000. This is equal to 10,000 centimeters squared is equal to 1 meter squared. Okay, so this is the conversion to change from centimeter square to meter square. This is our conversion. So you divide by 10,000. All right, so using that conversion, if we convert the 850 over here, we divide it by 10,000, we are going to get 8.5 times 10 raised to the power minus 2 meters as the area for area 1. So let's look at area 2. So for area 2, we'll have length times breadth as usual. For area 2, we can see that the length over here is 10 centimeters. The breadth is the 25 over here, which is the 25 here as well. Okay, so we can have 10 multiplied by 25, 10 multiplied by 25, and that will give us 250 centimeters squared. We divide that by 10,000 and we get 2.5 times 10 raised to the power minus 2 meters. Alright, let's calculate area 3. So for the third area, which is at the top over there, you see that the length over here is 34, and then the breadth over here is 10. So we have length times breadth, that is equal to 34 multiplied by 10, that is equal to 340 centimeters squared. Then if we convert that to meters, we'll have 3.4 times 10 raised to the power minus 2 meters squared. Meters squared, meters squared. Okay, so that is our area for area 1, area 2, and area 3 as shown in the diagram over here. Now that we have the area 1, area 2, area 3, let's proceed to calculate the pressure that each of these surfaces can exert on the ground. So let's calculate pressure 1. So pressure 1 will be equal to the force or the weight on area 1. On area 1, this will be equal to the force we were given to 25 newtons. On area 1 is 8.5 times 10 raised to the power minus 2 meters squared. And if we compute this into our calculator, we get 294.12, which to the nearest whole number is 294 Pascal. So the unit for measuring pressure is Pascal or Newton per meter squared. So our answer over here is 294 Pascal. Let's look at pressure 2. So for pressure 2, we have the force on area 2, and that will be equal to 25 on the area 2. The value we have is 2.5 times 10 raised to the power minus 2. And then if we compute this on our calculator, we are going to get 1,000 Pascal. So 1,000 Pascal. Now let's calculate pressure 3. Pressure 3. That is the pressure exerted by the surface area A3. So we will have force on area 3. So this is equal to 25 as the force on area 3. Area 3 is equal to 3.4 times 10 raised to the power minus 2. If we compute this into our calculator, we are going to get 735.29. So the nearest whole number is 735 Pascal. Right, so now that we have our answers, let's try and answer the question. So the question is saying, what is the greatest pressure and the least pressure? So if you look at it, we have 294,000 Pascal and then 735. So we realize that the greatest pressure is the 1,000 Pascal, and that is exerted by area 2, which has the area 2.5 times 10 raised to the power minus 2, which is literally the smallest area over here. So we say the smaller the area, the higher the pressure. So it makes sense that because the area is very small, it will exert the highest pressure. All right, let's look at the area with the least pressure over here. So if we look at that, between 294 and 735, definitely 294 is the least pressure. And if you look at that area is 8.5 times 10 raised to the power minus 2, which is the greatest area exerted by area 1. So we can see that area 1 has the biggest area. It has the biggest surface area. Because the area is big, the pressure that it will exert is quite small, and hence the reason why it has the smallest pressure. And if we look at area 2, area 2 has the smallest area, as we can see from the illustration, and hence the reason why it has the highest pressure, because the relationship between area and pressure is inversely proportional. All right, so let's have a look at another example to further appreciate what we are doing over here. Right, so we have a box of size 20 meters by 4 meters by 5 meters and has a mass of 120 kilogram. We are to calculate the least pressure that it exerts on the table, and II, the maximum pressure that it exerts on the table. So let's proceed with our solution. So let's write down our solution. All right, so we have a box of size. Let's write down the dimensions. So the dimensions are 20 meters. So likely we were given the dimensions in meters, so we don't need to convert again. And then we have a mass. The mass is equal to 120 kilogram. So we're told to calculate the least pressure and the maximum pressure, and then we're given gravity to be 10 meters per second squared. We know that pressure is equal to force over area. And then we know that force is equal to mass times acceleration due to gravity. So we can say pressure is equal to mass multiplied by gravity all over area. That will give us our pressure. Now let's try and have a visual representation of the box that we have or we were given in the question. So let me draw something very quick. So let's say this is our box. Okay, so this is going to be our 20 meters for the box, and then we have here to be our 4 meters, then we have here to be our 5 meters. Okay, so from the diagram we can see that let's make here area 1, let's make here area 2, and let's make here area 3. Now you can name the surfaces how you want, but make sure you know the result to multiply to get the area for each of those components. All right, so let's calculate the area for area 1. So for area 1 will be equal to length multiplied by breadth. And if we look at the diagram, our length will be 5, and then our breadth will be the top one over here, which is the 4 we have over here. So here to here is also 4 meters. So our area 1 is 5 by 4, and this is equal to 20 meters squared. That is our area 1. Right, let's look at area 2. Area 2. So area 2, we use the same formula, but our components to multiply will be different. So if you look at area 2, we have the length, which is 20 meters over here, and then the height or the breadth is 4 meters over here. So we have 20 multiplied by 4, and this is 80 meters squared. Right, let's look at area 3, the one at the top. Area 3. So this is equal to length times breadth as usual. But if we look at it, the length for area 3 will also be the 20 over here, but the breadth over here is this component over here, and that is 5. So we have 20 multiplied by 5, and that is equal to 100 meters squared. Now from the look of these areas, based on the area, because the force exerted is going to be the same, we can conclude on which area will have the highest pressure. So if you look at it, the smallest area here, 20 meters square, is expected to have the highest pressure, and then the highest area here is supposed to have the lowest pressure based on our understanding of pressure, the formula, and then the relationship between area and pressure. So let's see if this is actually true. So let's calculate pressure 1. So pressure 1 will be equal to Now let's calculate our force separately, so we just use it. So our force will be equal to mass times gravity, and that will be equal to our mass is 120 kilogram multiplied by our gravity, which is 10. So this will be equal to 1200 Newton. So this is our force. So our force is 1200. Right, so our pressure 1 will be force over area 1, and that will be equal to 1200 on 20. Okay, the 0 cancel, the 0 is left with 120. 2 will go into 120 60 times, so we have 60 pascal as our pressure 1. Now let's look at pressure 2. So pressure 2, we have force over area 2. Now our force is still the same, 1200 newtons on our area 2. We have over here is 80, so we have 80 here. 1200 divided by 80 will give us 15, so our answer is 15 pascal. Now let's calculate the pressure 3. Pressure 3, we have the same formula, force, but the area will be area 3. So this is equal to 1200 on our area 3 has 100 centimeters, 100 meters square as our area. So 1200 divided by 100 will give us 12 pascal as our pressure. So if we look at the results of pressure 1, pressure 2, and pressure 3, we realize that pressure 1 has 60 pascal, and it is the highest pressure, and the area over there is 20 meters square, which is the smallest area that we've seen among the three area 1, area 2, area 3. So like I said, the smallest area will have the highest pressure, and that is what we can see over here from the results. So the I aspect, the II, which is saying the maximum pressure that is set on the table, that maximum pressure will be from area 1, which has the smallest area, and that value, the pressure over there, will be 60 pascal. Now the I aspect, which is saying the least pressure between 15 and 12, 12 is the least or the smallest, so the least pressure is going to be 12 pascal, and it is exerted by the area 3, which has the highest surface area. All right, let's have a look at one final example, and then we end this beautiful tutorial. So the last example for this particular tutorial, we have a rectangular block with size 20 centimeters by 12 centimeters by 4 centimeters. It's made of a material of density 2 gram per cm cube. Find the minimum pressure it can exert when resting with one of its faces on a horizontal surface. All right, so let's have a look at the solution to this problem. Now we have a rectangular block with dimensions, so let's write down our dimensions. So our dimensions are 2 centimeters by 12 centimeters by 4 centimeters. And then we're told that it was made of a material with density. So the density represented by rho is equal to 2.0 grams per cm cube. We have to find the minimum pressure it can exert. All right, let's look at something. Now, in order for us to calculate the pressure, we need the force over the area. Now we know that from the dimensions we can get the area, so we don't have a problem. But the force, we can't find the force because we're given density. So let's break down force. We know that force is equal to mass times acceleration due to gravity. So we have mass multiplied by gravity, okay, on area. Now gravity, we know that gravity, okay, is approximately equal to 10 meters per second square. Okay, so which means that among all the parameters we have, or we are lacking, we have gravity, we can find the area, and then we are missing mass. So we need to find mass first. Now how do we find the mass? We know that density or rho is equal to mass over volume. Now, if you look at it, we have the density we're given, but we don't have volume. But we can get the volume of the block by using the dimension, multiplying all of them to get the volume. And then now that we have density and we can calculate the volume, we can easily find mass. So if we make mass the subject, over here, mass will be equal to the density multiplied by the volume, and that is equal to, the density is 2, so we have 2 there. Because the unit is in gram per cm cube, not kilogram per meters cube, I will not convert the density to kilogram per meters cube. I will maintain it like this because the units can cancel. So I have here 2 gram per cm cube, okay, multiplied by the volume. The volume will be equal to, into bracket, 2 multiplied by 12 multiplied by 4. So this is equal to 2 grams per cm cube. I want us to look at something. Multiplied by 2 multiplied by 12 multiplied by 4 will give us 96 cm cube. Sorry, cm cube, not negative, just cm cube. Okay, so from here we realize that the cm cube over here will cancel the per cm cube over here. So we are left with 2 grams multiplied by 96, and that will give us 192 grams. So this is our mass. But we know that for us to calculate density, our mass has to be in what? In kilograms. So we convert 192 grams to kilogram. To do that, we divide by 1,000. So if we do that, our mass will now be 192 divided by 1,000, and that will give us 0.192 kilogram as our mass. Right, so now that we have our mass, let's go ahead and calculate our force. So our force, which we said over here is mass times gravity, is again the same, mass times gravity. So let's look at our mass. Our mass is 0.192 multiplied by gravity, which, even though we're not given, we know is 10. And so if we do that, this will give us 1.92 newtons as our force. So now we are able to find that our force is equal to 1.92 newtons. All right, so now that we found the force, let's go ahead and calculate the areas, the possible areas from this dimension, and then we go ahead and calculate the pressures. Okay. Okay, so let's proceed. Now I will not be drawing the symbol or any diagram in this case, but let's calculate the area without necessarily drawing the illustration. So we will have area 1, which will be length times breadth. We will have area 2, and then we'll have area 3 as well. Now all of them will be length multiplied by breadth, length multiplied by breadth. Now for the first one, we can use 2 and 12 as the first one. So for area 1, let's say we have 2 centimeters multiplied by, now let me convert them straight to meters so that I don't have to convert later on. So the 2 centimeters, if I convert it to meters, it will be 0.02 multiplied by the 12 will become 0.12 meters, and then the 4 will become 0.04. okay, all of them is in meters, so this is their conversion. So area 1 will be 0.02 meters multiplied by 0.12, so I have 0.02 multiplied by 0.12, and that will give me 0.0024 meters squared. All right, let's look at area 2. Area 2, I still use 0.2, but I multiply with 0.04. So I have 0.02 multiplied by 0.04, and then that is equal to 0.02 multiplied by 0.04 will give me 0.0008 meters squared. Now if this multiplication I'm doing here is confusing you, you can draw a box yourself or a rectangular block and then give it the dimension yourself so that you know what to multiply. Now the last one will be between 0.12 and 0.04, so that will become 0.12 multiplied by 0.04, and that will give me 0.0048 meters squared. This will become my area 1, area 2, and area 3. Now if you look at these values, you realize that 0.0024, 0.008, and 0.0048, the smallest area among these guys will be 0.0008, and therefore it means that the 0.008 will be the one to exert the greatest pressure. Now if you look at the question is asking for the minimum pressure. So it means the minimum pressure, to get the minimum pressure, we need the surface area with the highest surface area. So if you look at it, 0.0048 will be the one to give us the minimum pressure. But let's go ahead and calculate the pressure 1, pressure 2, and pressure 3. But some students will just go ahead and make the deduction that because pressure is inversely proportional to the area with the highest surface area will give us the least pressure, and hence area 3, which has the highest surface area, will give us the minimum pressure, and then they will just do that calculation straight. But let's go ahead and see that for ourselves. So let's calculate pressure 1, which is equal to force on area 1, and the force we calculated earlier was 1.92 newtons on area 1, which is 0.0024, and that, if we punch that into our calculator, we are going to get 800 Pascal as our answer. Let's look at pressure 2. Now pressure 2, we will have force on area 2. Now this will give us 1.92 newtons for our force, and then our area is 0.0008, and then this will give us a pressure of 2400 Pascal. Now let's calculate pressure 3. It will be force on area 3, and that will be equal to 1.92 newtons on 0.0048, and that is equal to 400 Pascal if we punch that into our calculator. So if you look at the three pressures that we have over here, the minimum pressure among these three is 400 Pascal, and that was given to us by area 3, which has the highest surface area. So the highest surface area gave us the minimum or the smallest pressure. Like we said at the beginning of this video, we said that the higher the pressure, the smaller the surface area, and then the higher the surface area, then the smaller the pressure. So thank you so much for watching this video tutorial on pressure. If you like it, consider subscribing to the channel, like, share with your colleagues, and then I will see you in the next video. Bye bye. Hello and welcome to my science tutorials. In today's video, we want to look at pressure in liquids. So without further ado, let's begin. So what is pressure? We know that pressure can be defined as the force per unit area, that is the force per unit area, which means mathematically we can say pressure P is equal to force over area. Now when we talk about pressure in liquids, we are talking about the force per unit area that the volume of liquid exerts on the vessel or the container in which that liquid is. Now this force or this pressure that is exerted on the vessel is what we call the hydrostatic pressure, right? So For normal solids we just call it pressure, but for liquids we call it hydrostatic pressure. Now this hydrostatic pressure depends on three things, so let's look at them. So the first thing that pressure in liquids depends on is the density of the liquid. So we have density of the liquid. The second thing it depends on is the height of the liquid. So we are looking at the height of the liquid. And lastly, if we look at the last one, is the acceleration due to gravity. So acceleration due to gravity. So which means the pressure in a liquid depends on the density of the liquid, the height of the liquid in the container, and lastly the acceleration due to gravity of that particular liquid. Acceleration due to gravity, sorry. Now let's consider how the pressure that we are talking about depends on the density, the height, and the acceleration, whether it is directly proportional, inversely proportional, or how they relate to each other. Let's look at that. So we want to talk about the calculation of pressure in liquids. So calculation of pressure in liquids. Okay, so let me quickly get rid of these guys over here. All right, so let's say we have a container that looks like this, a very beautiful container, right? Obviously not drawn to scale, right? So we have from here to here is the height. This is the height, right, of the water in the container. We have here to be the area, right, the area of the container, and then we have the density or rho. This is the density. So we are to consider a liquid of density rho, which we have over here, contained in a vessel with a cross-sectional area A, right? So the area is in meters square, and the depth H in meters. All right, so let's look at some parameters. Let's look at the volume of the liquid, right? Now to get the volume of the liquid, we need to multiply the area or the base area by the height. Okay, so we use the area over here to multiply the height, and this will give us the volume, which means volume is equal to area multiplied by height. All right, now let's look at the mass of the liquid. So I'm going to represent this ml, that is mass of the liquid. So the mass of the liquid, we can obtain that from the density of the liquid. So we know density or rho is equal to mass, or the mass of the liquid, mass over volume, right? So if we make ml the subject, we are going to have density multiplied by the volume, right? But remember, we made the point at the top over here that the volume is equal to the area multiplied by the height. This implies that in place of the volume over here, the mass of the liquid will be density multiplied by area multiplied by height. Okay, now let's continue with our deduction. Now I'm going to erase this illustration over here, but it's actually very important. All right, now that we have the volume, now that we have the mass, let's look at the weight of the liquid. The weight. Now if you look at it, the weight of the liquid, or the weight, is mass multiplied by acceleration due to gravity. Okay, so which is m multiplied by g. But we know that the weight of the liquid, which is equal to mass multiplied by gravity, are you okay? The mass is equal to density multiplied by area multiplied by h. So in place of the mass over here, I'm going to have density multiplied by area multiplied by h multiplied by g. This is equal to weight. Now we know that weight is equal to force, right? Weight is the same as force, so which directly means that this whole thing that we have over here, which is the weight, is the same as the force. So the force is equal to the density multiplied by the cross-sectional area multiplied by the height and multiplied by gravity. Now let's make the final deduction over here. Now let's look at something. Now we said that pressure is equal to force over area. Now we agreed that the force we have, okay, or the force of the liquid is equal to the density rho multiplied by the cross-sectional area A multiplied by height and multiplied by gravity, all divided by area, which is A. So if we look at it over here, the area will cancel the area over here, and therefore our pressure will be equal to, the area has cancelled the area, so we have the density multiplied by height multiplied by gravity. So this is the expression that we want, or this is the expression that we are looking for, or we'll be using in our calculation. Remember, at the beginning of this video I said that the density or the hydrostatic pressure depends on the density of the liquid, the height of the liquid, and acceleration due to gravity. And this is the relationship. They are directly proportional to each other. Okay, so from the expression derived for the pressure exerted at the base, we realize that the pressure exerted depends on the height of the liquid column but not the area. Okay, so we can see that the pressure over here in liquids does not depend on the area, because there's no area in the formula over here, right? Unlike in solids, where it depends on the area. The smaller the area, the higher the pressure. In liquids, it does not depend on the area, but rather the height of the column or the vessel in which we find the water. So all right, so now that we have this basic understanding, we know that this is the formula that we are going to use to calculate our pressure in liquids. Let's have a look at some examples or some questions to further deepen our understanding of our concept, or of this concept, pressure in liquids. Right, so let's look at example number 1. So the base area, or the base of a rectangular vessel, measures 10 centimeters by 18 centimeters. Water is poured into a depth of 4 centimeters. What is the pressure at the base? We have to calculate the force exerted on the base. We have to take the density of water to be 1,000 kilogram per meters cube, and then gravity to be 10 meters per second squared. All right, so let's go ahead and look at the solution to this problem. So write down our solution. Okay, so we were told that the base of the rectangular vessel has a dimension, so I'm going to use the dimension to be equal to 10 centimeters by 18 centimeters. So 10 by 18 centimeters, right? So if I convert this straight ahead to meters, right, just so that I don't have to do conversion later on when I'm doing the calculation, 10 centimeters to meters, I divide by 100. So I'm going to have 10 divided by 100, that's going to give me 0.1 meters multiplied by 0.18 meters. That is the conversion for both that I have over here. Now water is poured into a depth of 4 centimeters. So the depth or the height is 4 centimeters over here, which is equal to, if I convert it to meters, I divide by 100, so that will give me 0.04 meters, right? And then we were asked what is the pressure, so we don't know the pressure, and we were told to calculate the force as well. We do not know the force. We were given the density of water, rho, to be equal to 1,000 kilogram per meters cube, and gravity, acceleration due to gravity, to be equal to 10 meters per second squared. All right, so let's go ahead and calculate the pressure for this particular problem. Now, if we look at the formula that we derived earlier on for pressure, we said pressure is equal to the density multiplied by the height multiplied by gravity. So there's no need we calculate area here. So if we look at it, pressure will be equal to the density is 1000, 1, 2, 3, multiplied by the height in meters, 0.04, then multiplied by gravity, which is 10. So if I compute everything into my calculator, 1000 multiplied by 0.04 multiplied by 10 will give me 400 Pascal as my pressure. So this is the pressure that I get. Now the second aspect of the question is saying we have to calculate the force exerted on the base. All right, so we know that pressure equals force over area. Okay, that's the normal formula. But we have the pressure, we know it's 400 Pascal, right? We're asked to find the force, which we do not know, but we can calculate the area from the dimension of the base given. So the area here will be equal to 0.1 over here multiplied by 0.18, which is going to give me 0.018 meters square as my area for the base. So now that I have the area of the base, and then I was asked to find force, I can make force the subject here. So making force the subject, I will have pressure multiplied by area. This is equal to, the pressure is 400 Pascal from here, and then the area is 0.018. So 400 multiplied by 0.018 is going to give me a force of 7.2 newtons. Okay, so this becomes the force exerted on the base of this particular rectangular vessel. All right, so now let's look at the second example. Example number 2. A tank is 1.5 meters deep and is full of water. We have to calculate the pressure at the bottom of the tank due to the liquid, given that the density of the water is 1000 kg per meters cube and acceleration due to gravity is 10 meters per second squared. All right, so this is a fairly easy example. So let's look at the solution. So we're given the height of the tank to be 1.5 meters. Since the water is full, right, it means the height of the water is also 1.5 meters. Or since the tank is full, the height of the water is also 1.5 meters. So the height here is the height of the water. So we have to calculate the pressure. So we don't know the pressure at the bottom of the tank. We're given density to be 1000 kilogram per meters cube, and then acceleration due to gravity to be 10 meters per second squared. Now we know that pressure in liquid is equal to the density multiplied by gravity multiplied by the height. That is for pressure or hydrostatic pressure. Now we know that the density over here is 1000, acceleration due to gravity is 10, and then the height is 1.5. It's already in meters, so it is very good for us. So if I multiply 1000 by 10 and by 1.5, I'm going to get 15,000 Pascal, right? Which is equal to 15 kilo Pascal or 15 bar. So let's look at another example to further understand this concept of pressure in liquid. Let's look at a very technical question. That's the third example. So this third example, I would like you to pay very close attention because it requires that we do quite a number of things, and you have to pay full attention and then use your head around the question. So let's go ahead and have a look at the question. So water from a leaking tap begins to fall into an empty tank of 0.5 meters wide by 2 centimeters long by 4 centimeters high. If the water drops, fall at a rate of 2 drops per second, and if each drop weighs 0.05 gram, after how many seconds will the pressure at the bottom of the tank be 200 Pascal? Okay, we're given the density of the water to be 1000 kilogram per meters cube, and then acceleration due to gravity as 10 meters per second square as usual. Right, so the first thing I do is I write down my solution, and then I collect the parameters or the things that have been given in the question. So the water from the leaking tap, okay, begins to fall into an empty tank of 0.5 meters wide. So the dimensions that I have is 0.5 meters wide, okay, by 2 centimeters. Sorry, this is 2 meters, so it's supposed to be meters, not centimeters. So it's by 2 meters wide, okay, and then this is also supposed to be in meters, so apologies for that. So it is 0.5 meters by 2 meters by 4 meters, right? That is the dimension that I have. So I was told if the drops fall at the rate of 2 drops per second, right? So the rate is 2 drops per second. So let me say rate is 2 drops per second, right? So let me make it 2D. So 2 drops per second. Per second is S. Okay, 2 drops per second. And if each drop, okay, a drop, okay, so the weight of the drop is 0.05 grams. Okay, after how many seconds? So where we have to find the seconds, will the pressure be 200 pascal? Okay, given that the density is 1000 as usual, and then our gravity is 10 meters per second squared. All right, so let's have a look at the solution for this particular problem. Now the first thing I would like to do before I tackle the question is to first of all convert my weight from gram to kilogram, or change all the units. Right now I've already corrected the fact that the units are all in meters, so not centimeters, so they are all in meters. That was an error when I was writing the question. So the only thing I need to convert over here to conform to all the units is the weight. So I need to convert it from gram to kilogram. Okay, so from gram to kilogram I need to divide by 1000. So if I divide 0.05 by 1000, I'm going to get, let me write it in standard form, 5 times 10 raised to the power minus 5 kilogram. All right, so that is my unit in kilogram. So now that I have this, I can go ahead and look at the question. Okay, so I know that pressure is equal to density multiplied by height multiplied by gravity. Now if I look at this formula, I know that I have my pressure, which is 200. I have density over here, okay? I have height. I was told that height is 4 meters. I have gravity. So this formula cannot help me get the seconds that I need. So I need to use another formula for pressure. So this formula will not do in this case. So now which other formula do we know for pressure? We also know that pressure is equal to force over area. Okay, now we know that force is what? Mass times gravity. Then we repeat our area. Now from here it means that we can get the total amount or the total mass of the water at 200 pascal. Okay, if we get the total amount or the total mass of the water at this particular pressure, which is the 200 pascal, then we can use that and use the rate of drop to calculate the seconds that we use to get this particular 200 pascal. So let me take that again. I said that in order for us to calculate the seconds, okay, that will give us the amount of seconds that has passed and how many or how much water is in the barrel or the container for us to have 200 pascal. We need to calculate the weight or the mass. Okay, let me be specific. The mass of the water in the tank, right? We need to calculate the mass of the water in the tank. Now if we get the mass of the water in the tank, that will give us an idea, since we have the rate at which it was dropping, then that will give us an idea of how long or how many number of drops based on the weight of each drop will give us the particular or the total weight or the total mass. Then we can use that to calculate the other parameters, which is the seconds that we're asked to find. So let's look at this. So pay attention. So we have the pressure, we know is equal to mass multiplied by gravity on area. Are you okay? So let's do the quick substitution. So our pressure is 200, we've been given here. Our mass we don't know, because that's the mass of the entire water in the tank that we want to find at the end. Okay, so we know gravity is 10, and then we know that area, the area over here, for us to calculate the area, I use the width and then the length over here, right? Not the height, right? The base, not the height. Okay, so I'm going to use 0.5 multiplied by 2. So I have 0.5 multiplied by 2, because the tank is going to be something like this. Okay, so this is the height, and then the wideness or the width, and then the length, right, will make the area at the base over here. So that is what I need. I need the width and the length, right? Not the height over here. All right, so from here I have 0.5 multiplied by 2, right, multiplied by 200. So I have 10m, that is from the top over here, will be equal to 200 multiplied by everything I have over here. So 200 multiplied by 0.5 multiplied by 2. So I have 10m is equal to 200 multiplied by 0.5, that will give us 100, multiplied by 2 will give me 200 again. So I now divide both sides by 10, and then my mass will now be, this will cancel this, so I now have 20 kilogram as the mass of the water at this particular pressure, which is the 200 pascal pressure. Now if the mass is 20 kilogram, we know that per drop is 0.05 grams, or 5 times 10 raised to the power minus 5 kilogram, and the total water we have in the tank is 20 kilogram. So to find the total number of drops that entered into the bucket, we need to divide the 20 kilogram over here by 5 times 10 raised to the power negative 5 to get the number in terms of drops, how many drops of water came to form this particular mass. So let's look at that. So the total mass over here, the total mass we have is 20 kilogram. So we have 20 kilogram. Then we divide that by the weight of one drop to get the total number of drops that we have in the tank. So we divide by 5 times 10 raised to the power minus 5, right? So number of, let me make this number of drops, nd, is equal to, now nd, number of drops, will be equal to 20 divided by 5 times 10 raised to the power minus 5 will give me 400,000. So I have 400,000 or 400k. So this is 400,000 drops, right, will give me this particular weight, which is 20 kilogram, and that 20 kilogram will give me a pressure of 200 pascal at the bottom. Now remember that the question is saying that we should find how many seconds, okay, it will take for the pressure to reach this. Now we know that it will take 400,000 drops, right? And we know the question gave us that 2 drops counts per second, right? 2 drops per second, 2 drops per second. And we know the total number of drops, right? We know that we have 400,000 drops. Now if I divide 400,000 drops by 2, that will give me the amount in seconds, right? That will give us this total of 200 pascal. So the seconds, the time in second, will give me, okay, let me make time in seconds, so let me make it ts, right? Time in seconds will give me nd, the total number of drops, divided by the rate. So our time in seconds will be the nd, which is 400,000, divided by the rate, which is 2 over here. So if I do that, if I compute this into my calculator, 400,000 divided by 2 will give me 200,000. So 200,000. So it means it is going to take 200,000 seconds for this particular drops one by one to fall into this tank to reach a mass of 20 kilogram and to exert a pressure of 200 pascal at the base of the tank. So thank you so much for watching. This is how we calculate the pressure at the base of a particular container or tank if we have a liquid in that particular container or tank. So thank you so much. This is how we calculate pressure in liquids, and I hope you found the video useful. If you do, kindly make sure you subscribe to the channel and turn on the notifications so that you don't miss any of the latest videos from my science tutorial. So once again, thank you, and I'll see you in the next video. Bye bye.